Hello, everyone. My name is Toghrul. I pretend to do research at school, but I usually just complain about things on Twitter. And today we're going to be talking about how we get to multisig-less rollups. And I'll explain more about what I mean by it in a bit. So, yeah, just remove the multisig. That's it. That's the entire solution. Thank you. No, I'm just joking. Let's go back. So let's start with this great screenshot from L2Beat. And it shows a lot of familiar names here: Arbitrum, Optimism, Base. There's Scroll underneath there. And there are a lot of red things, the color red in that pie, in all of those pies over there. So there's this nice scroll down menu there that you can pick, and it shows the stage of that you can pick and filter the protocols by. So let's do that. Let's pick stage 2. And let's see, oh, all of a sudden you only have 2 protocols. One is dgate, which is a ZK rollup that is application specific and is a DEX. And then there's Fuel V1, which is an optimistic rollup that does payment and has what, $953. Oh, it actually went up. It used to be $8. So great. Thanks, Bartek, for your contribution. And as I said, both of those rollups are application specific. So let's go back to the question: why is a multisig necessary? Or let's be more precise here: why is upgradability in general necessary for rollups? I think with app-specific rollups, you can get away to a certain degree without having a multisig. But if you're talking about general-purpose rollups, I think it's not a question, and I'll explain why it is later. So if you're a bit of a conspiracy freak, the answer would be the covert cabal wants to retain full control over the user funds. But I'm not a conspiracy freak, so I'll take off the tinfoil hat, and let's talk about the reasons why you actually need a multisig or upgradability. So one is security. And so you build a rollup, it's super good, it's super fast, it's super, the proving is super cheap. But what if there's a bug? Like, you don't want to be on this board, and this is incomplete. Like, a lot of the projects, Wormhole and stuff, are not on here that had hundreds of millions stolen from it. And as we know, smart contracts are complex, and with rollups, they're even more complex because you have the verifier, you have the bridge, you have a lot of different functionality than an average DeFi contract doesn't have. And so it's likely that there are bugs in there, and there are potentially bugs that can lead to catastrophic consequences. So, and to that, you must also add that you have provers. So in case of optimistic rollups, how many people actually understand the game theory behind how fraud proofs work and how they're implemented? Yeah, Bartek. 5? Ah, OK. Bartek says 5, so I trust him on that. And then on the zero knowledge side, how many people can actually audit the circuit? I would also say 5 here as well. So we almost treat both the fraud proofs and the zero knowledge proofs as black boxes and trust a handful of people in the world who can actually look at the code and audit and understand what it's doing, that they're actually paying attention at all time and didn't miss an important bug. And then the second reason why you want to have upgradability is feature expansion. So, for example, say you're building an EVM equivalent rollup. It's either an optimistic rollup or a ZK rollup. It doesn't matter in this case. So EVM equivalence requires you to expand the feature set in case EVM specification adds some new feature. Let's say a new cool opcode is introduced, or we get something that improves the fees, so for example, multi-dimensional fees, et cetera, in your EVM equivalent. So you want to support it. But to support it, you actually need to upgrade the code, on-chain code. So you need a way to upgrade the contracts. And currently, most of the solutions involve some form of multisig. But you might rightfully point out that, oh, yeah, but security councils are a thing. You don't need a multisig. But what is a security council? So like security councils are committees that have ability to initiate fast-track post-rollup contract upgrades. Like, it depends on a specific implementation of the security council. And it's usually it usually consists of external parties. So I think the definition of Security Council that LTB and Vitalik propose is that the maximum amount of core team members that can be on the Security Council is 25% of the entire multisig. And so it is a step in the right direction because it's not fully controlled by the team, but it's still a multisig. And a multisig is a multisig. Like, of course, you can argue that an external team might not be as easy to compromise as like a bunch of team members, but it's still an honest majority assumption. So essentially, you have a rollup that has all the tech underneath that allows it to have a trust minimized bridge that cannot have a trust minimized bridge because you have that multi-sig working underneath. And so I showed the graph before about where we filter out stage 2 rollups. So like, let's examine what a stage 2 rollup actually is. And specifically, we care about upgradability here. There are a lot of different things that require a rollup to comply with in order to be a stage 2. But in this case, a stage 2 rollup should allow users ample time to exit from the rollup in case there's a malicious upgrade. So what that means is, let's say if you introduce an upgrade, there has to be some time to allow those users to exit in case they either disagree with the upgrade for one reason or another, or it's an actual malicious upgrade. So, and typically we define ample time as 28 days. So that means that if you upgrade a bridge to either add a new feature or to fix a bug, which is even more pressing, because like with features you can wait for a bit, but like if you're fixing a bug that is critical and then that can result in funds being drained, this is not really a good option because by the time the upgrade actually is in effect, the funds might be gone. And so I lied a bit in the name because you can still have a multisig that initiates those upgrades, even though I expect the majority of the rollups actually use some form of governance to do that or the Security Council to do that. But it has to be delayed by 28 days, as I said before, at least 28 days. So how can you become a stage 2 rollup without compromising on security or future feature expansions? So there are a couple of steps here. One is multi-provers. So why should we have one prover when we can have multiple provers? And specifically distinct provers, because if you have two provers working with the same implementation and the same ZK system computing proofs, then it doesn't matter. You might as well just have one. So for example, you can combine Halo 2 prover with an SGX prover. So how it will work is basically you have those two provers working in parallel, and they submit the attestations and then also submit the state roots, the output state roots. And so basically, and the bridge compares those output state roots, and if the output state roots don't match, then it just halts and doesn't apply the state transition that corresponds to that state root. And basically what it allows you to do is to protect against correctness bugs in case there's a vulnerability inside one of the proofs. So you can think of it this way. This allows us to downgrade a correctness failure in case of a bug to an availability failure. Of course, if two of the provers have the same bug in them, then this doesn't really protect against that, but it's unlikely that you're going to have the same implementational bug in both of the provers. And basically, in this case, the bridge would halt, and you either let the governance choose what to do next, or have the Security Council pick the correct prover, which is much better than just having the funds stolen. But that's not really enough, because that only solves the problem with provers, but we still have the problems with smart contracts, the same problem actually. What if there's an implementational bug? And that's where multi-verifiers come in. So as with multi-provers, it's the same problem here. Why not have two distinct contract implementations? You can have more, but like, let's keep it simple for now and say two. So, and we also remember that aside from implementational bugs on the smart contract side, you can have contracts or the bytecode that results from a contract code suffer from a compiler bug. It happened recently with Viper and Curve, when certain curve pools were exploited because of a compiler bug. And so how would that work? How do you do that on the verifier side? So you combine two implementations. Say one is in Solidity and another is in Viper, and you have two implementations running in parallel. And the way it works is it basically protects you from both the compiler issues, but also diversifies the implementations, which means that you're not only protected from the bugs that you introduce, but also are protected from the bugs that are introduced on the compiler level. And to make it work, we need a minimal adapter contract that basically handles the checks, whether both of those contracts, say, as I mentioned before, like let's say in Solidity and Viper, are producing the same mutations. So for example, if two of them are trying to ask for a different slot to be changed, or like a different mutation to happen in storage within the same state transition, then it just rejects and it holds. And the same way it will work with a multi-prover. You convert, you downgrade a potential correctness failure that results in your funds being stolen to an availability failure that, again, can be either resolved through the governance or a security council. It's up to you how you sort that out. There are downsides to both of them, and basically the main downside is that both of them increase the cost of settling on Ethereum, which means that, especially right now when the cost is non-negligible as is, introducing additional cost, which will mean that certain users are going to say, like, why would I use you when I can use somebody else? And it's difficult to rationalize with a lot of people about the security features, the security properties that you introduce with that. But hopefully, as time passes, as Ethereum becomes cheaper to settle on, and we come up with better ways to optimize the costs, this becomes more and more viable. And we basically talk about implementational bugs, but that doesn't really touch on the specification side failures. So for example, you have the protocol specification, and it has an invalid statement in it that might result in funds being stolen. This doesn't protect against that. So what do we do there? So as I said, like, even if your implementation is completely bug-free, the specification can have some faulty statement in it. And that's where formal verification comes in. So if you combine the multi-prover, the multi-verifier, and formal verification, you get a system that is sufficiently secure where the probability of a safety failure is decreased to a point where the risk of having delayed upgradability is acceptable. Thank you, and feel free to ask questions.
Great, and thank you very much. So we have about 5 minutes to 10 minutes for some questions. So over here on the left.
Okay, so I have a question. Do you think that we could combine the fault proofs or fraud proofs with this system to reduce cost, meaning that you always go through one implementation and one prover, maybe not the prover, but the implementation, right? And then you give some time window. It doesn't necessarily have to be 7 days because there is no challenge game, right? Can we do that? Can we reduce cost in this way?
Yeah, I think that's definitely possible to build a more optimistic system. But the downside here is you're introducing game theory again, because there are certain things that you need to take into account, and also you're delaying finality, which I think is fine for now, but the more we go further and the more we actually get to the point where we can produce real-time proofs and have near synchronous composability between different L2s, that becomes a real downside. And I don't think you can shorten it to a point where the time difference is negligible. You still have to allow for like at least an hour or a few hours for this to work.
Great. Next question. Yeah, over here on the left.
Hi, thank you for the talk over here. Fundamentally, it looks to me from what you describe is that we don't actually get rid of the multisig, so we kind of still have some kind of a committee or some kind of governance that is fundamentally the multisig. So am I correct that basically we just decrease the share of edge cases where this multisig will be applied? Or like what's the fundamental difference to what we have now?
So let's say we refer to governance as multisig in this case. The multisig would only act in two different ways in this setup. One, in case they want to introduce an upgrade, but this is delayed, so we just need to allow the user sufficient time to exit in case an upgrade actually happens. And the second time when it's actually introduced is to break the deadlock, where let's say you have two implementations and one disagrees with the other. You introduce it to basically solve the availability failure. But what you can do instead of multisig there, you can actually have a third implementation working as well, so it acts as a tiebreaker in both. It's just a bit not very viable right now because it'll take a lot of resources, but I can see in the future how you can have two primary implementations working all the time, and then the third implementation acting as a tiebreaker in case one of them fails. So I think I would agree that the title is a bit misleading. You still have multisigs, but you don't have them acting in the same capacity that they do now. Thank you.
Thank you.